Nice to meet you all. My name is Àlex. I'm from PySchool, and I will be presenting the project Earth Virtual Expert, EVE, which we are doing in collaboration with Imperative Space and the European Space Agency's PhyLab. So first, I will give you a little bit of an overview of the project in general. Then I will describe a bit more specifically the data that we've used in the project, then the work on the actual training of EVE, RAG, factuality and tools, how we are evaluating, and a recap. So EVE is a suite of open source agentic LLM assistant, which is based on Mistral 3.2 24 billion, and several specialized datasets for Earth observation. We developed this under the ESA PhyLab's AI for EO initiative with a €1 million funding, and the assistant will be accessible via web platform and API. The gist of it is that it's an Earth observation assistant that will answer natural language queries with trusted insights. So it's capable of explaining Earth observation concepts in natural language question answering. It's capable of guiding users to relevant EO trusted sources by RAG. It's capable of summarizing scientific documents, and it is connected to several web and external tool collections to deliver insights on trends and applications. So since I am not a domain expert, and probably a lot of people here are not, just a quick idea of what is Earth observation. Earth observation essentially is any kind of discipline that collects information about Earth using satellites, drones, or ground sensors. This is typically used for things like monitoring climate change, tracking deforestation, changes in agriculture, urban growth, things like this. Can also be used to respond to natural disasters or support policy decision-making. So one of the first things to clarify is that as it stands right now, EVE is trained on text only and structured text, essentially. And the idea is for it to be essentially a research assistant, for the most part, to the EO domain. And the vision-specific capabilities are coming in a later future improvement, and also from agentic connection to specialized visual models separate from EVE itself. We started the project a bit over a year ago, last May, and we are expected to end it this coming November with a 1-month pilot that will be open to the public between October and November, and afterwards, between late November and December, the API and the web access will be fully open to everyone. This is work that I'm done with other colleagues from PySchool. Marcello and Vish are here with you today, and also other colleagues from Imperative Space and ESA PhyLab as well. Here, the domain experts are mainly ESA and Imperative Space. PySchool, really, we are doing mostly the AI and the NLP work. So, as a bit of an overview then, the tangible contributions essentially of EVE is first the model itself, domain-specific and instruction-tuned LLM into this domain, the curated Earth observation and more related Earth sciences corpus of data, of raw data, the synthetically generated instruction datasets in the EO domain, some manually created evaluation datasets, both instruction fine-tuning for the instruction following and the hallucination, the training and the recreation workflow and recipes, and the actual accessible chat interface, as I said, hosted on ESA PhyLab. And last but not least, also the legal and compliance documentation needed to gather the data, be able to know that we can open source it, etc. The audience, for the most part, is twofold. So on one hand, we have scientific experts in the domain. So imagine you're a PhD student doing environmental science. You want a specialized assistant that will aid you, for example, in your new paper that you're writing. It will be connected to a variety of trusted sources, some including private sources from the European Space Agency, for example, that will not be online. And it will also be connected to other auxiliary tools. Also for non-specialist users, so imagine you are an NGO, or you are a policymaker, or you're a journalist. You don't want to go too deep into these concepts, but you want to have a specialized model in this domain. So, when a disaster happens, to inform environmental policy, etc. So this is the overall idea of EVE, both the training and the inference. So I'll go over it step by step. So first we start, you can see my cursor, yeah. First we start with an open weight LLM, which, as I said, is Mistral 3.2 24 billion. And the first thing we do is we fine-tune it. So for this, we take some Earth observation domain data This is mainly peer-reviewed papers and other trusted sources. And we do a synthetic generation based on that, concluding in an instruction fine-tuning dataset. So we mainly focus on question, answer, and summarization, and a bit of tool usage. This we also pair with replay data, so general domain data that the model has already been pre-trained on to avoid catastrophic forgetting. And we do instruction fine-tuning. I will go more in depth later. This results in the instructed LLM proper, already specialized more on Earth observation. And then with a set of preference data, copying the same idea of Earth observation and general domain preference data, we perform alignment, which results in the final model itself, the aligned LLM that the user actually sees. After that, when the user inputs a query, the model is connected to several tools. Some are going to be databases, some are going to be other tools like Code ID or a calculator, etc. And the output of these tools is integrated with the model into the actual model output that the user sees. So regarding data, which in many ways for a project like this is quite important because we are essentially starting almost from scratch. There's very little curated corpora in this domain accessible. First, we have our main corpus, which is 5.7 billion tokens of open access data on the scientific EO domain. So mainly this is peer-reviewed papers, but also sources from ESA or national space agencies, things like this. Through a special licensing agreement, we also got 1.1 billion tokens closed access papers from Wiley. And we have some authentic instruction data. So we create around 5,000 QA samples, and we assemble around 100K summarization samples using the abstracts in the papers. And the bulk of the work here is the creation of the actual synthetic SFT data, which I will explain more in depth later. We also create some manual preference data, and we create a large RAG database mainly coming from this corpus here with around 300K articles and documents. We also have two smaller test sets to check on factuality and red teaming. So this corpus essentially we create by manually identifying high-quality trusted sources, so journals and things like this. That part is completely manual. And then we just design a custom pipeline to do the web scraping and the extraction of the text and structured text, so algorithms, formulas, tables, etc. And we do processing consisting of cleaning, duplication, and personally identifiable information removal. To this, we also add some filtering of some domain-relevant content that we get from large-scale datasets. And we enrich these documents with useful metadata like journal, year, citations, etc. And both the corpus, the actual final processed corpus, and the code base to handle it, to create it, are going to be open sourced at the project's end. And the corpus looks something like this after processing. So overall, we get 5.3 billion tokens, of which around 1 point something are closed access. That's the blue line right there. Everything else will be open access. And they come from a variety of trusted sources in the domain, and as usual, a relatively long tail in the distribution. As well as this curated corpus, we also create some authentic EO instruction data. So we have around 20 to 30 annotators, mainly coming from academic background, so from undergraduate to PhD students. And we create 5,000 samples across several datasets, so question answering, factuality, preference, and a little bit of rate teaming. This authentic dataset we mainly use for evaluation, but a little bit also for grounding the generation of additional synthetic data. And on this work, mainly on the previous one regarding the creation of the corpus itself, we ensure that we remove all the personally identifiable information so that later on we can be compliant while releasing the resulting corpus, so removing names, emails, phone numbers, etc. We only take, of course, the permissive or legal secure sources that we can use, and we keep a registry to ensure source attribution later on when we use these sources. So now we have the curated corpus, we have it cleaned, we have it enriched with metadata, and we have a small amount of authentic SFT, manual SFT data. So now we can start actually fine-tuning the model. First of all, you could ask why, because if you're going to connect it to a RAG database and so on, there's a good argument that you could say maybe a vanilla model just works as well and there's no need to go through the fine-tuning. Well, there is enough literature that shows that when you do it well, domain-specific LLMs can often match and sometimes outperform generalist models, mainly on technical domains. The fact that we can use a smallish model means that, which will be open sourced, of course, means that the community later on can do essentially whatever they want to it. They can quantize it, they can fine-tune it, they can do their own custom deployment relatively affordably. And while we are developing this, we are always checking on the actual manual evaluation on the real EO scenarios that we create to check whether the fine-tuning that we're performing actually is improving on the benchmarks or not. So initially we started more than a year ago on the Llama family with the idea of starting some experiments with the 8 billion model and then moving to the 70. Eventually we shifted to Mistral 3.2 24B as a result of a collaboration with Mistral as well. This resulted in using a slightly larger architecture for us, very close to state-of-the-art within its size range. It's an open-weight European model, which for the European Space Agency is also an important plus. It's trained with React, so it's already capable of tool use. It has tool usage capabilities. It has some RAG-specific pre-training, mainly in terms of like the citation-specific tokens. And because it is already integrated with a visual encoder, it opens the door relatively easy in the future for a potential multimodal EO extension, where we to fine-tune the encoder into the domain. So we have the raw corpus, we have the choice of the model. The idea now is to create synthetically a large data set of instruction data. So the idea here is that we want structured data that we're going to create with an LLM, but this creation, we want to ground it somehow. If you go to an LLM and you just say, generate 100,000 pairs of question answers in Earth observation, I think that after a while, the results are not going to be very satisfactory. The model will start hallucinating, it will not be grounded on anything, essentially. So this grounding essentially can come from two different places. One is something a bit like self-instruct, which is giving it authentic instructions. So you already have a seed pool of instructions. You few-shot the model, essentially, to generate a few other instructions that will look like the authentic ones that you are giving it. Alternatively, you can ground the generation on the authentic context. That means, essentially, I will give you a RAG-like setup, so a chunk that I have retrieved from somewhere, or an entire document or whatever, and I will ask the model to actually generate the QA pair grounded on that paper, or on that chunk, or the collection of chunks, or whatever it is. Again, the objective here is to minimize, essentially, the hallucination of the model. So the way we do it is by defining a pool of models that we use, which we randomly sample to serve both as generators as well as evaluators. And with this, we can create a synthetic QA dataset, which is of hundreds of millions of pairs, around 1 billion output tokens, more or less. We maximize diversity by changing the amount of chunks, the amount of authentic context that the model can see to generate the samples, the relevance of chunks, so sometimes the chunks are very relevant to each other, sometimes not so much, and sometimes we even give adversarial context, so we explicitly give the model incorrect chunks that have nothing to do with one another, so that the model can learn that not all the chunks that it will retrieve from its database are necessarily going to be useful always. And to this, we also add some data replay, as I said before, to avoid catastrophic forgetting. We don't want to overfeed too much to the Earth observation domain, because ultimately it's still a chatbot that people want to be able to use in a seamless way. So this is one of the processes that we do to generate the synthetic data. So we start with a document, we chunk it, and then we have a critic model that's essentially just a model trained to give some quality scores, mainly on issues like fluency and things like that. So the idea here is that, for example, if one of those chunks is mainly comprised of the bibliography of the paper, then the score is going to be lower because it's not very interesting to generate a question out of the bibliography of a paper. Likewise, if a chunk is mainly the title and the metadata of the paper, it's probably not very interesting. But if a chunk mainly contains a lot of technical information, that is the chunk that you want. So from those scores, we take a filtered subset of the scores for each paper. And then essentially we just use similarity on the vector store to retrieve similar chunks from other papers that essentially will talk about the same thing. With that multi-context of chunks, we will do structure generation of question answering with an LLM, and with another LLM, we'll evaluate the output. This evaluation is mainly done on a variety of criteria, mainly whether the question is self-contained within the context, how technical it is, how relevant to the domain it is, etc. And then that after the rationale that the LLM as a judge outputs, we ask it just a structure generation of integers, and we usually take only the perfect the samples that the evaluator judges as 5 out of 5. That is one pipeline. We also have another pipeline where we start from an entire document, so a very long form, long context QA. We also have some refusals, so we explicitly generate model, get the model to generate unanswerable questions again, with the idea that we want our model that when it doesn't find the relevant information in the RAG to say I don't know, rather than make something up. Multi-document is what I just explained, and some identity basic model information dataset. In addition to QA, we also train on summarization. For that, we assemble abstract as summary datasets. So, you take the entire paper, you take the abstract of the paper, that's the target, that's the summary. Obviously, this is not very diverse because you always have the entire paper and the entire abstract. So we also do multi-section generation. So sometimes we generate synthetically some summary of a relatively small section, sometimes a larger one, sometimes from the beginning of the paper, sometimes from the end, etc. And as I said, we use the LLM as a judge final part of the pipeline in both processes. That is the bulk of the synthetic generation for the SFT. And then we have the final part of the training, which is the preference. So the preference dataset looks something like this. So you have usually some kind of like prompt, and you have some preferred or winning response and some losing response. We do some authentic preference annotation. So for that, we pull responses both from the already fine-tuned instructed model, as well as some manually created responses, as well as responses from other models. And then we just get human annotators to label preference. And then we also generate some synthetic dataset following the pipeline from ultra feedback. So we take some already existing pool of instructions, we take a large model pool, and from each instruction we generate a variety of answers, and then we have a judge that will just simply rank them, essentially. Then with those scores, you can just binarize the output by choosing, the preferred versus all the other non-preferred. And with this, we can do alignment. So we end up with around 1,000K samples of the authentic ones, as well as the replay data that we also add once more to avoid catastrophic forgetting, and we do it by direct preference optimization. The actual fine-tuning, which is something that we are carrying out right now because we are still under the development of the project, we are doing experiments on LoRa with R8 to R32 experiments, and we are essentially doing batches of SFT and DPO. So we do a little bit of SFT and a little bit of DPO. We monitor the dev set, and we continue like this, creating data and monitoring the signals on the dev set. While we are doing this, I don't have any results yet to show about this, but we are still monitoring which models are more or less impactful on the training to balance the pool on the generator, the sampling, of the generator models. All of this compute is mainly done on Mare Nostrum ACC partition, as well as various private cloud computing, so Roundpod, Lambda Labs, and Mistral fine-tuning. And the main usages, probably in terms of quantity, essentially is the synthetic data generation and evaluation, then the fine-tuning, and then various miscellaneous of the data processing and things like that. So as I say, we're still in the development, so the numbers are not fully exact yet. There's some estimates around there. But for the synthetic generation, we mainly used Mare Nostrum, and we're probably going to do from 4 to 16. It's a bit of a large range, but sometimes it's hard to estimate GPU hours by API calls. This should result between 25 and 35,000 GPU hours. For the fine-tuning, we're mainly using managed Mistral fine-tuning, which will result in 5 to 10K GPU hours, and means that the total compute of the project, essentially, without counting inference, of course, will be between 30 and 45K GPU 1,000 hours, which is equivalent to around 3 to 9 tons of CO2. So with this, we have the fine-tuning done. And now we have the last task, essentially, of connecting the model to external resources. Due to our use case, the main one is, of course, RAG. I think more or less you all know how RAG works. We have a variety of data sources. We do a relatively standard cleaning procedure. We chunk it. We have an embedding model. For the embedding model right now, we are using one developed by NASA called Indus, which is especially fine-tuned for scientific applications. And we upload the triple of metadata, chunk, and embedding into a vector database. The query of the user is then embedded in the same model. We do some similarity search, and we retrieve a variety of documents. We integrate it into the prompt template, and we give it to the model for the output. We also introduce this other module here, which is something on top for fact-checking, which I will go more in depth now. So the databases, we have several. We have one that is the main one, which is the one that we built from the open access corpus that we scraped, that we cleaned, which is 270K documents, not points. Then we have another one, which is closed access from Wiley, which is 67K documents. Then we have a private collection that only authenticated users can access from ESA directly. Each user then has its own private collection. And then we also have an online connection to some curated sources as a fallback as well. The embedding model, I think I already explained. For the chunking, we do a mixture of hierarchical chunking and length-based chunking. So due to the process of the data, all of the data that we have is in Markdown, which means that we have these hierarchical labels to know what is a section and what is a subsection. So we do a mixture of splitting by structure, as well as further dividing or merging chunks if they are too far apart from a desired length. So more or less all the chunks are similar length, but there is some variability. And then finally, for each paper, we extract the main metadata that we want, pretty straightforward, the URL, the title, etc. This is the fact-checking module that I was explaining before. So here we are zooming in on this part here. Once we have the retrieval from our databases or the web sources, we are giving it to the model and we get an output. That's the normal stuff. Then we're giving it to an LLM, which right now we are still experimenting which one works best. So right now it's a bit agnostic, this. And this LLM, using a mixture of either uncertainty or consistency, if we're talking about the same model, uncertainty will just basically mean perplexity, and consistency will mean consistency of the output over k runs, or LLM as a judge will output both a flag saying, this output is a bit suspicious of being hallucinated or not being grounded on the context that I have seen, and a hypothetical set of spans of the output that are particularly the focus that might be hallucinated. If we don't have the flag, then we're happy with the output and we give the output to the user and that's it. If we have the flag, then we do a reprompting of the queries. So the idea is, imagine you have 3 spans that you are suspected of being hallucinated. You create 3 different queries to focus specifically on each of those. The idea here is then you do the retrieval normally. The idea here is that the documents that you are now going to be retrieving are probably going to be different than the initial ones, because the user query initially may not have been explicitly talking about these topics either. So you do the retrieval with the new queries. If all goes well, you should have a lot of relevant documents that you didn't, or chunks that you didn't have before, and essentially you start again, right? If you have done this more than once, then essentially you reprompt a bit the model this time to do a bit of a self-reflection style prompting, and then you give the two outputs, the original one and the new one, to the model as a blind ranking. We're still experimenting, as I say, but right now this results in like a 70% of the model just choosing the loop 1 versus the loop 0 generation, and it seems to work relatively well, albeit, of course, as you can imagine, it increases latency quite a bit because it's a relatively lengthy loop. So as I said, the model is already, the Mistral 3.2 is trained with React, so it's capable of using tools. And in our case specifically, we have various MCP connections. So we have the ESA database that I described, the private one. We have the closed access one, as well as our main open access one. And the idea is that we are retrieving seamlessly from all of the databases at the same time, actually plus the user private database there that is missing should be there also. And then we just re-rank from the entire retrieve chunks from each of the sources, looking for just semantic similarity first from the original query, but also source reliability, authority, quality, and recency. So, a paper that has, 500 citations and is from last year, probably more trustworthy than a paper with one citation from 10 years ago. In addition to the databases itself, we also have some citation graphs. So essentially, a graph where papers are connected to each other based on how the papers cite each other or not. And some web search on some curated sources, that are not necessarily peer-reviewed papers. And also in the future, we're going to add other auxiliary tools, calculators, code ID, connection to Hugging Face for, models, datasets, etc. So the evaluation essentially comes in two different forms. First, in terms of the general domain, and then in terms of a specific domain. In terms of the general domain, we just simply evaluate on the standard benchmarks. It's not very different. And we also check some perplexity on selected high-quality unstructured text. The idea here is mainly to monitor that we are not losing too much of the general capabilities. We are okay with a little bit of a trade-off, but that's the main idea. And then we have our actual target domain, for which we create all of these datasets manually. So we have an open-ended QA dataset, as well as a multiple-choice QA dataset. We also have an hallucination factuality dataset to evaluate the actual factuality detection capabilities of the model. And we have a couple of small preference and red teaming sets. A red teaming set is just an adversarial set. So, you have an adversarial prompt and you have a expected versus preferred output, essentially. These use the standard metrics. So for the raw text, we use perplexity. For the structured datasets, we use accuracy, exact match, intersection over union for the more extractive QA tasks. We also use, although it's not super important, some linguistic metrics, embedding based and syntax, and the one that has the highest correlation to human judgment is LLM as a judge for sure. And we also have, as I said, a little bit of manual preference evaluation as well as red teaming. So this is a little bit the project. I will give a final kind of overview. So I touch a bit the different points that I described. So first, we are building this domain-specific LLM, specifically for Earth observation and Earth sciences. With it, we also create or assemble these both authentic and synthetic datasets. So first, the 5 billion token corpus from open access scientific articles, as well as similar trusted sources, the both synthetic and authentic question answering dataset, summarization, the preference datasets, hallucination mitigation of factuality, and the red teaming. The model is capable of using tools. It's already connected to several scientific RAG databases, some web connection, and auxiliary tools, as I described a bit before. And we perform evaluation both on general as well as the EO-specific target domain benchmarks. And the entire pipeline during project end will be open under ESA File Lab with both web and API access. And all of these elements of the pipeline will also be open sourced in Hugging Face. And that's essentially it. So as I said, there is still some development of the project, that is still going on. So end of September, probably 1st of October, we will start a 1-month pilot, which I encourage you all to register. So, we are going to gather feedback from the people. We're going to hope that you break it as much as possible during that month so that we can fix it before the actual opening. And then in November, we will essentially wrap everything up. We will open source everything, and we will have the actual assistant properly up on the ESA website. And that's all for me. Thank you very, very much. I think we still have 5 minutes, so you can ask some questions now if you have them. Otherwise, also, you can catch either me, Marcello, or Vish outside also. Thank you very much. Yeah, I don't know if there is an order. Yeah.
Thanks so much for the talk. Have you tested it against state-of-the-art models of today's? So how much it compares, how much the time that you have spent is adjusted to how the performance is differs between the big models from big providers?
Yeah, we are still doing this. It's an ongoing thing because, as I said, we're still doing the fine-tuning. The main focus, I will say, is on a comparison on similar sizes, right? So, we're talking about 24 billion, so, between, 5, 7, 8 to 30, 70 maybe. Compared with very large providers, I don't think we are still doing the final test right now because we're monitoring more the fine-tuning, but it will be part of the final benchmark. Yeah, I don't know. Yeah, you? I don't have them on the slides, but yeah, I have a couple but they are still a bit, work in progress. So one result that I have is, I think I already said, how often the model chooses the preferred one, which is 70 or something like that. Then we also are still testing on how to do the detection either on a binary way, just the output seems hallucinated or not, or the span-specific one. So we have a 2K sample dataset, which is nice to actually get some scores. On binary detection, the results are fairly decent. We are getting a 75 F1 score, something like that. On span, we're still not finally yet. I think that the correlation that we have right now is 0.4 or something like that when we do it at span level. Yeah, I think you were before, yeah.
Well, thank you for the talk. I have a couple of questions. First, and it's probably been on a slide that I missed, but what's the proportion between authentic and synthetic fine-tuning datasets?
Oh, for actually fine-tuning? Oh, there's almost no authentic fine-tuning. Okay. For the authentic data, mainly we're using for, wait a second. The authentic data, we are mainly using, you can call it authentic, the summarization ones that are created from abstracts, I guess, in a sense. But otherwise, the majority of the authentic data for the instruction, we're doing it for either the pool for preference that I said, ultra feedback style, or the actual evaluation. So in terms of the actual fine-tuning proper, almost entirely it's synthetic.